Good morning, dear students. Welcome back to my electrochemistry class. Today I am going to discuss about the two anomalous behavior, the two phenomenon, that is the dispersion of conductance behavior of the electrolytes. That is the anomalous the conductance shown by the strong electrolyte. That is I am going to discuss today. That is the other is called, they are called a dispersion of conductance exhibited by strong electrolyte, especially at two different conditions, one at high potential and the other at a very high AC current. So, let me discuss the dispersion of conductance. That is, it is actually the deviation of the conductance behavior of the strong electrolyte as against the theoretical Debye-Onsager theory. That is, an electrolyte does not shows the decrease in conductance as given by or are explained by the Debye-Onsager theory. Here it has an anomalous conductance. So that you have to discuss dispersion of conductance or anomalous conductance of strong electrolyte. There is anomalous behavior. One is Wien effect. The first point, the first phenomenon is one, the Wien effect. Wien effect. Okay. W-I-E-N, Wien effect. That is, as all of you know that the mobility or the conductance of a particular ion in a strong electrolyte is slightly reduced by the dragging force of the unsymmetrical ionic strength just behind the moving ion that arises from the asymmetry of the central ion under the application of the applied electric field that I have mentioned. Similarly, as the central ion moving forward direction, the ionic atmosphere with its attached water molecule has a tendency, solid molecule has a tendency to move in the backward direction or the opposite direction, so that it offers a frictional force, a frictional resistance, thereby reduce or drag the ion, that thereby reduce the ionic mobility and hence reduce the conductivity. That is the electrophoretic effect. Okay. So, but the situation is slightly different. When normally, that is, at a low applied voltage, the ionic mobility do not change considerably or do not influence considerably by the application of the applied field. Generally, we can say that an applied voltage only causes the migration of the ion, or it gives only the directional characteristic of the electron. It does not produce any ion, but some way it will affect the speed of the ion. Under the condition of a low voltage applied voltage, the speed of the particular ion, that is characteristic of the particular ion, okay, that is does not change considerably. But okay, it changes only very slowly. The speed of the ion is generally very low. On applying the applied potential, the speed of the ion changes only very slowly, by minor change only, so we usually neglect it under a normal voltage. But when we apply a very high voltage of the order of 10⁵ volts, so under an applied voltage of very high 10⁵ volts, that is very high voltage. Okay, this is normally, you know that 50,000 volts. 1, 2, 3, 4, 5. 10⁵, 50,000 volts. Okay. nearly. Okay, 5 lakhs volts there. This in this range, 10 raised to 5, 1, 2, 3, 4, 5. In this applied voltage, okay, in this high applied voltage, 10 raised to 5 volts per centimeter, okay, the ion attain a very high speed. Usually the ionic mobility is of the order of 10 raised to minus 6 centimeter per second. Okay, the usual mobility of the ion, but under a very high voltage of 10 raised to 5 volts per centimeter, the ion attain, okay, and attain 10 raised to meter per second, attain with high speed of 0.1 meter per second. So under the high voltage, you remember normally the ionic mobility is considerably small, that is the order of 10 raised to minus 5 meter per second. Usually, and a slightly somewhat higher speed is shown by mobility is shown by h plus ion. The explanation I will be given later. But when we apply an high voltage of 10 raised to 5 volts or 5 lakhs voltage greater, the ion attain a high speed of very high speed of 0.1 meter per second. Under this high speed, so that what I want to say is that when we apply a high voltage of the order of 10 raised to 5 volt per centimeter, the ion attain a very high speed of the order of 0.1 meter per second. Under this high speed, the ion practically travel a much greater distance from the effect of the ionic atmosphere just behind it, because the thickness of the ionic atmosphere is only 1 nanometer or 0.1 nanometer. The thickness of the ionic atmosphere is only 0.1 nanometer. This is the speed of the ion. Speed of the ion at high voltage. This is the thickness. Thickness of the ionic atmosphere. So what you have to look into the aspect. Under a high voltage, the ion can travel a much longer distance compared to the thickness of the ionic atmosphere, so that practically the ionic atmosphere is not going to drag the ion that is moving with a high velocity, so that the ion does not need to produce the new ionic atmosphere on the direction of its motion, and also the ion is completely away from the electrophoretic effect. Practically, these two effect vanishes under a high voltage. So at this stage, the electrolytic conductivity, the ion, accepted by the ion, is much greater than that required by or that suggested by the de Broglie-Onsager equation. And this increased conductance of the electrolyte shown by under high voltage of 10 raised to 5 under high voltage of the order of 10 raised to 5 volts is called the Wien effect. So that is the definition is very simple. That is, the high conductance shown by the strong electrolyte as against the de Broglie-Onsager theory. Okay, as from the general observation, at a very high voltage greater than 10 raised to 5 volts per centimeter is known as Wien effect. That's the definition. Once again I repeat. The high conductance, electrical conductance shown by the electrolyte solution under a very high applied voltage of the order of 10 raised to 5 volt per centimeter, okay, is known as Wien effect. It is against the general observation of the strong electrolyte. And explanation is that under a high voltage, usually we can say that the potential with respect to applied potential, the velocity of the ion changes. It is better only very slowly. But under a high voltage, the velocity of the ion changes considerably. That is, under a high voltage, the ion travel at tremendous speed considerably of the order of 10.1 meter per second. But the thickness of the ionic atmosphere just behind the moving ion is only 0.1 nanometer. So, under the high voltage, the ion can travel a much larger distance from the thickness of the ionic atmosphere, so that that ionic atmosphere practically has no influence on the ion that is moving on the forward direction, so that the dragging force arising from the asymmetry of the ionic atmosphere vanishes. Also, the electrophoretic effect vanishes, and hence the ion has a mobility and hence conductance much higher than that normally expected, and this increased conductance at high voltage is called the Green effect. That's all. The next is, second is the Debye-Fagenheiten effect. Debye-Fagenheiten. Okay. F-A-K-E-N, Fagenheiten. Debye-Fagenheiten effect. Here also an increased conductance is observed at what condition we have discussed. Both are the increased conductance. What is that? Wien effect and Debye-Fagenheiten effect are the increased conductance shown by the strong electrolyte as against the general behavior of the general conductance. When we apply an alternate high frequency AC current under the application of high frequency alternating current, AC current of the order of 10⁻⁹ cycles per second. That is called mega cycles. The order of mega cycles. Then we apply the electrolyte to the action of an AC current of megacycle, that is to 9 cycles per second. Under this condition, the moving ion does not get sufficient time to build its own ionic atmosphere on the direction of the motion, because before that, the direction of the ion changes. As you know that AC current is this sine. It's like a sine, where it changes sign. Depending on the sign change, which takes place within a time of 10⁻⁹ megacycle. So at a high frequency, AC current of the order of 10⁻⁹ cycle per second. Under this voltage, under these cycles, 10⁻⁹ cycles per second, you know that the direction of the current changes much speedier than, with much shorter than time of the relaxation time. The relaxation time is of the order of 10⁻⁻⁶ or 10⁻⁻⁷ seconds. But here it takes place within a time of 10⁻⁹ seconds. So under a high frequency AC current, the sign of the electric bulb changes within a time of 10⁻⁹ seconds, much lesser than the time of relaxation of the ionic atmosphere. So under these high cycles, frequency cycles, high AC frequency, the moving ion does not get sufficient time to build its own ionic atmosphere or the direction of the motion. Practically it means that it is practically free from its own ionic atmosphere. Similarly, it is practically free from the electrophoretic effect. Hence the ions exhibit a much higher conductance than their normal behavior, and this increased conductance shown by the ion in the solution at high frequency AC current is called Debye-Fagenheiten effect. So the two effects. One is under a high applied voltage. The ion exhibits a high electric conductance than the normal behavior, normal conductance. That's called Wien effect that I have explained. This is the fact that ion can travel a much longer distance. Okay, 3 or 4 times greater than from the ionic atmosphere. So practically it does not feel any driving force from the ionic atmosphere and also the electrophoretic effect. So it can exhibit high conductance. Similarly, under a high frequency AC, the sign of the current changes within a short time of 10 to minus 9 seconds, while that of the relaxation time is 10 to minus 6 seconds. So the ion will not get sufficient time to produce its own ionic atmosphere in the direction of the motion before the change in the sign of the electric current. Hence, the ion feel that practically there is no ionic atmosphere and practically no electrophoretic effect going to drag the ion, and hence it exhibits a high conductance. And that is called Debye-Falkenhagen effect. I hope that you have followed me. So these aspects will be asked for your examination in the 2 marks. Okay, any one of them. What is Wien effect? What is Falkenhagen effect? Both are the increased conductance of strong electrolyte shown than its normal conductance as required by Debye-Falkenhagen segregation. One is at high voltage and the other is at a high frequency AC current. You remember the magnitude? The magnitude of the voltage is 10 to 5 volts per centimeter. The magnitude of AC is 10 to 9 cycles per second, or megacycles. Megacycle or megahertz, okay. The next is, let us pass on to the term ionic mobility transport number. Okay, now important aspect I am going to discuss the ionic mobility and the transport number of the ion and the determination of transport number. In your syllabus, we have to discuss 2 different methods. One is the Hittos method for the determination of transport number, and the other is the moving boundary method for the determination of transport number. Both method is very important according to the syllabus, so it may be asked for an essay for your examination. So first of all, we have to discuss, define the ionic mobility. You know that under an applied voltage, the ions which are free can migrate towards the opposite electrode, or ions are moving towards the opposite electrode with a definite particular speed that is characteristic of the cation and the anion. Okay, and also the speed of the ion slightly changes with the applied voltage. Therefore, we should have a term called ionic mobility to represent the speed of the cation and the speed of the anion, or speed of the ion generally under an applied voltage. That's the reason we are using the concept called ionic mobility. So, ionic mobility is a term. Ionic mobility, okay, that is U plus or U minus, is a term used to represent speed of the ion in its solution. So first thing, you have to study this fact. Ionic mobility is a term used to represent or indicate the speed of the ion in solution. It is usually represented by U plus or U minus. U plus speed of the cation, or ionic mobility of the cation. U minus is the speed or ionic mobility of the anion. And ionic mobility, because the speed of the ion slightly changes with the applied voltage. So the ionic mobility is defined as the distance traveled by the ion per second under an applied voltage of 1 volt per centimeter. Okay, this is the definition. Distance U plus or U minus is defined as the distance traveled ionic mobility is defined as the distance traveled by the ion per second under an applied voltage of 1 volt per centimeter, or it can be SI system. This is a CGS unit system. In SI system, it's the distance traveled by the ion. Okay, in SI, okay, this is in centimeter per second. In SI system, it is the distance traveled by the ion in meter per second under a voltage of 1 volt per meter. So anyone you can use. SI unit is meter per second and 1 volt per meter. Therefore, the unit is U plus or U minus. The unit is the distance, that is centimeter second inverse divided by volt by centimeter. That is equal to, centimeter square. Centimeter, your 1 by centimeter. Volt per centimeter. So 1 by centimeter square, volt inverse, second inverse. So the unit of ionic mobility is centimeter square, volt inverse, second inverse, or it is meter square, volt inverse, volt inverse, second inverse. So the unit of ionic mobility is centimeter square, volt inverse, second inverse, or meter square, volt inverse, second inverse. So it is a distance traveled by the ion per second under an applied voltage of 1 volt per centimeter or 1 volt per meter. Generally, we have to say that the magnitude of the ionic mobility is considerably small. That is the order of, generally, this is the order of 10 raised to minus 5, 10 raised to minus 6, 10 raised to minus 7, etc. meter per second. Usually. But considerably, the ion, or that depends on the nature of the ion. That depends on the nature of the ion. NaCl, the speed of Na plus, the speed of the nature, it says peculiar between Na plus and Cl minus. Similarly, in the case of HCl, the speed of the H plus, U plus depends on H plus and the speed of the Cl minus. Similarly, copper sulfate, here also 2 plus, 2 minus. So all these ions differ in the ionic mobility or the speed depending on the nature of the ion. Generally, larger ions are mobility is much smaller than that of the smaller ion. Generally, so you can say, but the H plus ion, the mobility of the H plus ion and slightly OH minus ion is much greater than any other ion. The H plus ion, the ionic mobility of H plus ion is much greater than any other ion. And also considerably OH minus, but H plus is much greater than any other ion. It is due to the hydrogen growth type mechanism. That is, in aqueous solution, the H plus ion is attached to the water molecule. In this form, H plus hydronium ion. So the H plus ion in the hydronium ion attached to the water molecule can form a bridge, hydrogen bridge, by the OH minus ion of other water molecule, like this. And this can then again transported to this movement is transported or transmission or transmitted to the all other water molecule like this. Okay, like this. So this is called a growth type mechanism. GROTTHUS, growths, GROTTHUS, growths type mechanism. I'll explain. The abnormally high ionic mobility of H plus ion is due to the transference of H plus ion through the hydrogen bonding attached between the water molecule, or they transmitted, the H plus ion is transmitted through the various water molecule in the form of hydrogen bonding or hydrogen bridge. Because H plus ion is attached to one molecule so as to form hydronium ion. The H plus ion from the hydronium ion can form a bridge or create undergo transfer to the other water molecule by the hydrogen bonding bridge, and this is transmitted continuously towards the all other water molecule, and this takes place very quickly, and that is why this facilitation give rise to the high mobility of the H plus ion. That's called growth type mechanism. Then, how to define the transport number? Number of ion. That is, transport number of the cation T plus and transport number of the anion T minus. Okay. The transport number, you know that the ion migrate or move through a particular solution, electric solution, with a particular velocity under the influence of an applied electric current. Okay. When we pass a definite quantity of electricity through an electrolytic solution, the ion in the particular electrolyte move with a particular velocity towards an opposite electrode. The cation move from anode to the cathode. That is the situation. The cation is moving away from the anode to the cathode. Similarly, the anion is moving away from the cathode towards the anode. What is actually happening is that due to the movement of the cation away from the anode and the movement of anion away from the cathode, there occurs a decrease in the concentration of cation around the anode and a decrease in the concentration of anion around the cathode. Don't get confused. That is, generally there occurs the decrease in the concentration of a particular ion around a particular electrode that are moving away from the electrode. Okay, that is the situation. That is around each electrode there occurs a decrease in the concentration of the ion, decrease in the concentration with respect to the ion that is moving away from the electrode. That is the general situation. Okay. You know, as the result of passage of the current, the cation move away from the anode by carrying current. Then we have to think out what is the fraction of the current carried by the cation. Similarly, on passing electric current, the anion move away from the anode and moving towards the cathode with a definite carrying a definite quantity of current. What is the quantity of the current? You know that when we pass a definite quantity of the current, that is the total quantity of current, that current is split between or shared between the cation and the anion. That is actually happening. What is the amount of the current carried by the cation depending on its nature? Similarly, that gives its mobility. Similarly, what is the fraction of the total current carried by the anion that determines its anionic mobility depends on the nature of the anion. And the transport number of an ion is defined as, therefore, the fraction of the total current carried by a particular ion. That is always equal to the ratio of the speed of the particular ion to the total speed of the cation and the anion. So that is the fact you have to study. So I am going directly to what is transport number of an ion. Transport number of an ion is defined as the fraction of the total amount of the current, the fraction of the total amount of the current carried by the ion. So, transport number of an ion, okay, T of an ion, transport number of an ion is defined as the fraction of the total amount of the current carried by that ion. We have only two transport number. One is the transport number of the cation, T plus, that I mentioned. Another is the transport number of the anion. Therefore, transport number of the cation T plus is current carried by the cation. Current is the ratio of the current carried by the cation divided by total current. Total current is the equation. Similarly, the transport number of the anion is the current carried by the anion divided by the total current. It is always a fraction and is not equal. And when we pass a particular quantity Q of current through an HCl electrolyte solution, HCl solution, nearly about 80%, 84% of the fraction of the current is carried by H plus ion, while the remaining 16% is carried by the chloride ion. So we have to say that 0.84 is the transport number of the H plus ion, and 0.16 is the transport number of the anion, chloride ion here. So that depends only on the characteristic of the ion or nature of the ion. That is different for different electrodes. Therefore, because since ionic mobility of an ion changes with its nature, transport number of the ion also changes accordingly or directly. Okay, accordingly. And you remember, transport number is the fraction of the current carried by the particular ion, and this T plus is the current carried by the cation divided by total current. And the transport number of the anion T minus is current carried by the anion divided by the total current. And as I already mentioned, the current carried by a particular ion is proportional to the speed of the ion. Okay, that is proportional to the speed of the ion, U plus. So the T plus, the current carried by the cation is U plus, and total current is U plus U minus. Similarly, the transport number of the anion T minus is current carried by the anion by total current, that is equal to, we can equate it, is equal to U minus divided by U plus U minus. So, this is the situation. So you can define transport number as like this. The ratio of the ionic mobility of the cation to the total mobility of the cation and the anion, that is the transport number of the cation. Similarly, the transport number of the anion is the ratio of the mobility of the anion to the total mobility of the anion and the cation. But usually, this is a method used to define the transport number. It is fraction of the total current carried by a particular ion. And always you know that since it is shared between the cation and the anion, sum of the transport number is always 1. T plus T minus is always 1. Therefore, once T plus is known, then T minus 1 is. Okay, T minus. Okay, T minus is T plus T minus is 1. Therefore, T minus is 1 minus T plus. What I wish to say is that there is no need for a separate experimental determination of the transport number of the cation and anion. You have to determine the transport number of any one of them experimentally. Okay. Then once the transport number of a particular ion is determined experimentally, then we can calculate the transport number of the other ion by subtracting that from 1. That means T plus is known experimentally, okay, determined experimentally, then T minus is 1 minus T plus. That's all. So in connection with the transport number, you have to study this ratio. Okay, once again, the transport number of a cation is the current carried by the cation divided by the total current, and that is equal to U plus divided by U plus U minus, because the fact that the current carried by a particular ion is proportional to the speed of the ion. Similarly, the total current is also proportional to the total speed of the ion. Okay. Similarly comes the conductance. You have a lambda plus. Similarly, lambda plus lambda minus. Okay. What I want to say is that the amount of the current carried by an ion is proportional to the speed of the ion. Therefore, the total current carried by the electrolyte is sum of the cation and anion mobility. So we can split this equation as the fraction of the total current carried, the transport number. Fraction of total current carried is divided as U plus divided by U plus U minus, and also U minus divided by U plus U minus, that is the transport number of the anion. Okay. And the total transport number T plus T minus is 1. Then transport number or transference number, both are the same. Transport number or transference number. Again, you have to remember another point that I mentioned in connection with the electrolysis. When we are passing electricity through an electrolytic solution by introducing 2 electrodes, the one electrode is called anode and other electrode is usually called cathode, depending on the polarity, depending on the polarity, or depending on this positive and negative terminal to which the electrode is connected. One is called the positive electrode anode, and the other is called negative electrode called cathode. On passing electricity through the electrolytic solution that I mentioned, that is, the cathode has a tendency to move towards the cathode away from the anode. So the cation are moving away from the anode towards the cathode. And similarly, under the influence of the electric field, the anion has a tendency to move away from the cathode and moving towards the anode. Once again, under the influence of the electric field, the cation has a tendency to move away from the anode and move towards cathode. Therefore, there occurs a fall in concentration of cathode or with respect to cathode around the anode. That's an important. Similarly, on the other hand, on passing electricity, the anion always move away from the cathode and move towards anode. So there is a falling concentration of the anion around the cathode. Around the cathode. Therefore, you have to remember, you see, therefore the falling concentration around the anode, the falling concentration around the anode. Falling concentration occurring around the anode is proportional to the speed of the U plus cation. Okay, speed of the cation, that is the ion moving away from it. Ion moving away from anode. Okay. Similarly, the falling concentration around or in vicinity, I means in the vicinity around. The falling concentration in the vicinity or around, both are same. The falling concentration in the vicinity of the anode around anode is proportional to the speed of the ion, speed of the cation, that is ion that is moving away from the anode, that is cation. Similarly, the falling concentration around or in the vicinity of cathode, around cathode, is proportional to the ion moving away from it. Proportional to the ion moving away from cathode. You know that? That means the ion moving away from the cathode. Okay, from the cathode, that is moving away from the cathode, that is moving to its anode, it is anion. Proportional to the speed of the anion. Okay, that is falling concentration of the anode is proportional to the speed of the cation, that is U plus. Similarly, the falling concentration around the anode cathode is proportional to the speed of the anion, that is U minus. Therefore, the total fall in concentration, is proportional to U plus U minus, that is proportional to the total current. And you know again, the falling concentration around the anode is proportional to U plus. Okay, U plus, that is proportional to speed of the U plus. Okay, that is a fraction, that is the current carried by the, okay, that is the current carried by the amount of the current carried by the cathode. Similarly, the falling concentration around the cathode is proportional to U minus, that is the fraction of the current carried by the anion. Okay, therefore the total falling concentration is proportional to U plus U minus is the total current carried by the anion. Therefore, you have to know that the transport number of the cation T plus can be determined by simply measuring the falling concentration around the anode and the total falling concentration. Okay, simply by knowing. So you have to remember, that is, the equation can be modified as transport number T plus of cation is equal to fall in concentration around the anode. Falling concentration around the anode. Okay, falling concentration around by total fall in concentration. So experimentally, the transport number of cation can be determined by this technique. If you can measure the falling concentration around the anode and the falling concentration of cathode and anode, then by dividing that falling concentration around the anode by the total falling concentration, okay, then it is possible for us to determine the transport number of the cation. Once transport number of the cation is determined, the transport number of the anion is 1 minus T plus. And this is the principle that is employed in the Hittor's method. Hittor's method, H-I-T-T-O-R. Hittor's method for the experimental determination of the transport number of an ion. So, the principle behind the Hittor's method, the principle behind Hittor's method, Hittor method, Hittor's method for the determination of the transport number of an ion depends on this fact, that is, the transport number of cation is equal to the fraction of the total current carried by the particular ion, that is equal to fraction of the total current carried by the particular ion, that is equal to current carried by ion divided by total current, that is equal to U plus divided by U plus plus U minus, and that is equal to falling concentration around the anode divided by the total falling concentration. Similarly, the transport number of the anion can be determined. That is equal to falling concentration around the cathode divided by total falling concentration experimentally. So that is the principle employed for the Hittor's method for the determination of the transport number. This experimental part will be discussed in the other class. So thank you very much. I am going to wind up the class. So thank you very much for my listening by class. I hope that you have followed me, the points that I have, that in various aspects that I have introduced before you. Okay, thank you very much.